discuss about the data encryption standard or DES. Data encryption standard or DES. So DES, okay. So DES is the technique where encryption can be done on the data, and here in this scheme we can learn to review the history of the DES, how this DES has been developed, then the basic structure of DES, and describe the details of building elements of DES, and to describe the round key generation process and to analyze the DES. And now come to the introduction section. So in the data encryption standard is a symmetric key block cipher published in the National Institute of Standard and Technology, NIST. So what is the story behind this DES technique? So in 1973, NIST published a request for a proposal of the security scheme. That means what is the current scenario, how the security can be made on this crypto system. So they request a proposal from the basic people and from the technical persons, and that proposal has been submitted by the IBM, and they developed some technique that was a project under the IBM, which is called the Lucifer, and this was accepted as a DES, and then DES was published in the Federal Register in March 1975 as a draft of the Federal Information Processing Standard FIPS. So basically this technique has been developed by IBM, and their project name was Lucifer. So this is a now quite standard technique. Nowadays people are using this DES technique for the encryption method, to use the encryption for public data encryption. Now this DES is a basically block cipher, and the basic architecture or basic semantic diagram is shown here. First, on the encryption and decryption of the DES, we have to choose 64-bit plain text, 64-bit plain text, and 56-bit key. Means you have a secret key of 56-bit, and for the message what you want to encrypt, that message should be minimum 64-bit, and for the 64-bit plain text you have to take this 64-bit as a block. Suppose you have a 1-page or 2-page message, then you just break this in a ASCII bit format, and you just block by block or a 64-bit block you just collect, and then you try to encrypt using your 64-bit secret key. Then it becomes a DES cipher. After that, this 64-bit cipher, you can send this cipher to the receiver end. Then receiver will receive the cipher, and then he decrypt the message using the 56-bit key. So this is the plain text. Okay. Now what is the basic structure of the DES? The encryption process is made of 2 permutation pbox, which we call initial and final permutation, and there is a 16 crystal round. Already we have discussed on the previous class that what is pbox and how this crystal round has been made using the pbox. And again we will discuss few points on the pbox and how this crystal rounds has been used to encrypt the message using DES. So there is 2 permutations, beginning and end of this system, and then there is a 16 rounds. So within the 16 rounds you can encrypt your message 16 times, basically you can say that, or more than that. But every round, so many factors has been involved to encrypt the message. Now coming to the details of this DES scheme. Here, the DES scheme, this is the general structure of the DES. You observe there is a 64-bit plain text you have to collect from the plain text message. Then you apply this technique, the DES, where the first is called the initial permutation, and at the end, after 16 round, there is a final permutation. So there is a permutation means you just change the position of the bit pattern, and then during this total DES encryption scheme, you can use some key generation technique where 56-bit cipher key has been taken as a key for encryption, and then this 56-bit key, some bit has been discarded, and we take the 48-bit session key for each round. So the first round we take 48-bit key. Then for the second round, again we take another 48-bit key, means you can generate some another 48-bit key using this 56-bit key. And in this way, K1 to K16, so basically several 16 keys are used to encrypt the message. And round where there is also 16 round. And before the round start, there is an initial, and after that there is a final permutation. And finally, when the message bit has been traversed from this initial permutation rounds using some key, then finally we can get 64-bit ciphertext. So this ciphertext, there is no relation between the plain text and ciphertext, that is the confusion and diffusion can be achieved more higher. Now the question is how this initial permutation can work, how this round on has been worked, so how the key generation can be designed. So we are coming to the next step. The first of all, the initial permutation and final permutation is shown here. See the technique here. You have a 64-bit key initially, and then you just change the position. The first bit will come to the 40, then second bit will come to the 8, and in this way, we say 58-bit position bit will come to the 1. So we just permute the positions using some table, okay? And you have to keep secret of this table. If you have this table, then you can do the encryption and decryption. So initial permutation is that, see here what we can write in the table. So we can write the position. Say the 58 will come to the first. So we have to write 58. That means we have to write in this way. This is the initial permutation 58. So what do you mean by that? Means the 58 bit will come to the first position of this permutation. Then 50 means what? The 50th position bit will come to the second. 42 means the 42th position bit will come to the third. So in this way, we can permute the data. So if you don't have this table, then you cannot say how this can be done. There is all of 64 bits are 1010, but we have changed the position according to this table. What is the meaning of table? 58 means what? The 58th bit will come to the first position. 50 means the 50th bit will come to the second position. So in this way, if it is the final initial permutation, then obviously there should be a final permutation, and these are vice versa. That means what? The 58 position bits will come to the 1, so 1 bit will go to the 50 positions, like this. So there is a initial permutation table, and you have to keep secret this table because this is one of the secret key. If you don't have this table, so no one can decrypt the message. Okay, this is the first part. So the initial and final permutation are straight pbox, means 64 bits are initially are there in the input level. So obviously we have a 64 bit in the output level. So that are the inverse of each other, means you can get the previous one, means you can get the original ones. So they have no cryptographic significance in the DS, because using this technique you cannot, there is a encryption, because no cryptographic significance is there. There is no diffusion confusion relation is there. If you have the key, then obviously you can decrypt. So there is no significance. So only it can be changed the position. So now next one is called the round. This is very important for the round. So what is this round? Round means we can encrypt the message using 16 rounds, and each round of the DES is a crystal round, crystal cipher. What is this crystal cipher? See, this is the basic design of the crystal cipher. You have to remember this one, very important. You have a 64-bit pattern. First we divide this 64-bit into two parts. First one is 32-bit, which is called the L, left, and 32-bit is called the right. Then we have used, this is the round. On the round, there are two things. One is and the swapper. On the mixer part, there is a function which is RI1, means this part, with K1. K1 is the key. So using the key and right side bit, we apply a function. After passing the bits from this function, this bit will go and perform the XOR operation with the left side, and that will go to the swapper on the left hand side. And on the right hand side, this bit will directly go to the swapper. So basically, swapper have the left side and right side part, and this swapper will interchange this part, means you just send the left side to the right side and right side to the left side. So this again 32 bits, you can get the left and right part. Okay, have you any question for this? Do you have any question? So many questions are there, like what is the basic function of this f? What is f? How this can be done? Clear? So we are coming to this part. So this function basically called the heart of the DES. DES, this function is the heart of the DES, which is a DES function. So the DES function apply 48-bit key to the rightmost, 32-bit to produce to a 32-bit output. So this f of R and K1, this is called the function of DES, and this is the heart of the DES. And then how this operation has been performed, what things has been done in this function part. So I am coming to this explanation. That is, you have a 32-bit on the right hand side, then you apply the expansion P box where 32-bit has been expanded into the 48-bit. Now again question arises how this can be done. I am coming on the next slide. But here in this function, this 40, so consider this 48-bit can be generated easily, and then 48-bit will XOR with the 48-bit key. So 48 and 48 is same, so nothing complex will be there. You can do the XOR because there is a 48-bit in a input level and 48-bit key are there, so you can perform the XOR operation. After this performing this XOR operation, we have used some S box, and on the X box, this 48-bit will give as a input, take as a input, and generate a 32-bit output bit stream. And this 32-bit will again passes to the straight P box, and get the 32-bit data. So these all functions will be done within the function of this DES. Now there are several questions arises to your mind that how this expansion pbox can be work, what is the function of HBox, how can be done on the 48-bit to 32-bit, again what is the function of state pbox, how it can be done, what is the significance. So all these have been discussed on the next slide. See, first one come to the expansion pbox. So this is the expansion pbox. You have a 32-bit input and 48-bit key. So we have to convert this 32-bit to 48-bit. So this is the expansion permutation. You have a 32-bit, so you just divide into 8 blocks, 4-bit, 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 and in this way 32-bit. Now for this each 4-bit block, there is a 5-bit, there is a 1, 2, 3, 4, 5, 6, 6-bit can be generated. So what is the significance or how this can be generated? So first, you take these 4-bit to 4-bit positions, and for the first position, you take this 32-bit position in the first position, and for the 6th position, you take the first bit of the next block. Okay, first bit of the next block, you take this one, and on the second block, the last bit of the first block will be taken, and then you just put the 4-bit, and in this way you take the next block bit and put into the 6th position of the next block, and this bit will go to the first bit of this next block. So in this way we can generate 6-bit data from the 4-bit. Then what will happen? 6 are 48. So 48-bit data we can generate from this 32-bit block. So this is the first one, expansion pbox. Then the next function is, this is the next function. Then we have used the next block. This is called the pbox basically. So see, in our main design, first one is the expansion, then we have used the pbox table. So on the expansion pbox table, this is basically nothing different. This is the expansion pbox table what we have discussed just earlier, that 32-bit will come to the first, then 1, 2, 3, 4, and 5th position will come to the 6. So these are the 6 bits will generate from the 4-bit, 1, 2, 3, 4. And again on the next block there is a 5, 6, 7, 8, and the 4 will come to the first bit and 9 will come to the next bit. So each block there is a 6 bits which will generate from the 4-bit. So this is expansion pbox basically, nothing else. Then only there is a XOR. So after expansion pbox there is a 48-bit key you have only from the 32-bit, and we have a 48-bit key. Now we perform the XOR operation. So this is nothing else. You just easily can perform the XOR. Then you have apply SBox. What is the SBox? SBox is there is a 6-bit. From the 6-bit you have to convert into the 4-bit. So in the input level you put the 6-bit. This is 6-bit, 1, 2, 3, 4, 5, 6, and from each 6-bit you just get the 4-bit. So this is possible using the SBox, and there is a total 48-bit. So basically we have 8 blocks, and from 8 blocks each block take the 6-bit and generate 4 bits. So we get the 32-bit from the 48-bit. Now again question arises how this SBox can be generated. See, this is the structure of the SBox. First you take the bit 1 to 6, and from the first bit and 6th bit will take here, and I will give you perform the index. If these two bits are 0 0, then it is 0. If it is 0 1, then first one 1 0 and 1 1. 0 0 0 1 1 0 1 1. You just write this one. And other 4 bit which is belonging to the middle we take as the index of the table on the top, that is 0 0 0 0, then 0, 0 0 0 1 1, 0 0 1 0 2. So in this way you can get the 15 data bit, 15 indexes. So there is a 15 index, there is a 15. And for each block you can take a table entry where for each table entry you can write some bit, and for each table content 4 bit. So this is the 4 bit. If you give the input as a 6 bit, then in this way from these 6 bits you can get the one single cell has been selected, and in the single set there is only 4 bit data. Okay, so easily we can convert from 6 bit to 4 bit. So how this table has been shown look likes. This is the table from 0 1 2 3 and 0 1 2 3 15. Suppose you give an input as a there is a say 2 and 7, then obviously from this table you can find 11. So how this 2 is 7? There is 2 means 0 1 and 7 means 1 1 1. So this if 4 bit pattern on the 2 and 7. So 2 means what? First you have to write 1, then the 0 at the end. So 1 0, then 7 means 0 1 1 1. So 1 0 1 1 1 0. So for this particular bit you can get some value 11. So if you don't have this table, so no one can decrypt. So this table is another table which is called the secret for the encryption. And then straight pbox has been used finally. So this is a straight means what? You have a 48 bit to 32 bits, and there is a 32 bits straight pbox, and from this 32 bits straight pbox you just convert this easily. You can do that. What does the meaning of this 16? That is which value are there in the 16th position, that will come to this first position. 7, the 7 positions input will come to the input bit will come to the second position. So in this way you can get another state permutations. So what will happen? Do you have any idea how this can be done? So this is the whole structure of the DES. Lots of things have been done, lots of performance have been done, say permutation, then expansion, then XOR, then SBox, then PBox, then again permutation. So your bit will be changed a lot. So you cannot recognize, you cannot understand, you cannot get any relation between the plain text and ciphertext. So this is basically DES, and you have to remember in your mind, and you have to write in the exam also. And this is the first approach was there to achieve this goal. One approach is to make the last round 16 on the difference, and then again there is a mixer and shopper. So people use no shopping on the last round. That was the first design. Now this is the design C. Observe, 64-bit keys are there, then input permutation, then it is round 1, K1 has been used, then round 2, K2 has been used, and in this way up to 16 round there is a final permutation, and for this final permutation we get the 64-bit. Now so many people can ask why this is 16 permutation, 16 round, because they have design. Not sure that the 16 round will get the good, not like that, but they have designed the up to 16 round, and they have shown that when you design this one up to 16 round, then it will be quite tough to decrypt the message. But on the receiver side, when this decryption message has been received, encrypted message has been received, then they have just do reverse on the which are done on this sender side. So we are converting to the initial permutation, then use the round 1, round 2, round 3 with same key, reverse in reverse. So this is in this way 16, and in this way it finally go to the last round, and then finally for final parameters you can achieve the 64-bit plain text. Okay, so this is the design of the DES, and so many there are pseudocode also there, you can do that, and so many alternate approach also has been developed. I'm not coming to the because this is the reduced syllabus, so just simply you just learn how DS has been done. And then some key generation is one important, how this can be possible to generate of 48 bit key to the from the 56 bit key to the 48 bit key, because there is another question that we have taken is a global key 56 bit, but when we perform within the DS we have used 48 bit key. Now question arises how it is possible. Okay, so for this reason we can show that this is the key generation scheme. I just try to explain. First one, you have 64-bit key, then you apply this 64-bit key on a parity drop box, and on the parity drop box hello ক্লাসে আছি আচ্ছা আচ্ছা আমি ক্লাসে আছি then you have to apply this parity drop bit, huh? So this is a key with the parity drop is 64 bit, then the parity drop, this can be drop this 64 to 56 bit key. Then after that there is a 28 bit key, though there is a shift left and shift left has been used. So both these shift left we can get again 28 and 28 with it is compression of p box, and from this compression of p box there is a round one key has been generated. So that is from this 64 bit key we just shift first and then it convert into the compression p box. Then after compression, you know that compression means what, from the 64 থেকে 56 bit. So this 56 bit key then again compression, that means it will become 48 bit key. So this from the 56 to 48 bit key has been generated. Again left shift both and 28 bit key, then compression p box, and you get the 48 bit key. So in this way, every time it has been performed the left shift and then compression p box, and then you get the 48 bit key. So in this way, each time we can achieve the key. And see how that shifting has been generated or can be done. This can be used this round and shift. So here 1 2 9 6, if these rounds we are used, then only the one bit will be shift. So in the first round, after the when you use first round, then shifting will be one bit. When you use two round, second round, then shifting will be one bit. When 9 round, then it will be one bit, and when the 16 round, it will 1 bit. Other all these rounds have been done by the 2 bits key, 2 bits shift. Is it clear? Okay. So 64 bit key, you drop some bit, get 56 bit key, again divide into two parts, then you apply in the compression box, and the compression will generate 48 bit key. Again you shift, and this shifting has been done for according to this table. If it is a round 1, then 1 bit. It is round 3, then 2 bits. Round 4, then 2 bits. So in this way you can do the shifting. And each after shifting you enter the 56 bit to the compression box. Compression box will generate 48 bit. Now question arises, how this compression box can generate 56 to 48. Okay. So this is the first one is the parity drop. Drop some bit. See, some bits are missing there. The number of bits shift. This is the table. And then key compression table. This is called the 48 bit key from the 56 bit key. Okay. And this is the key generation has been completed. Now I will not discuss about the DS analysis, because just we have to learn how the DS has been worked and how the key generation has been worked. Okay. Now, do you have any questions? Then we can discuss these questions. Have you any question? Do you have any question? কোশ্চেন যদি না থাকে তাহলে আমরা পড়ে দেখো, যদি কিছুটা বুঝে থাকো বুঝো, বোঝার পর আমাকে কোশ্চেন করবে। ওকে, Okay, thank you.